Welcome. Today I'm going to talk to you guys about power. And power is kind of like work, kind of one of those concepts that you have a pretty good general understanding of it, and you use that term every day or pretty often. But from a physics perspective, you have to be very careful about how you use it because it has a very particular meaning. And it's a meaning actually that you probably are familiar with, although you don't know it. And so we're going to go ahead and try to explore that just a little bit here. The concept really bases itself off of work, and so I'm going to just put that up there again. The formula for work, and I'm going to go ahead and put that, I'll put it over here so that we can remember it. Remember that work is equal to the amount of force that you do multiplied by the displacement of the object as a result of that force. And just a reminder that those two are both vectors, and they both are going for us, either going in the same direction or going in opposite directions. If they're perpendicular to each other, we know that the force could not have caused the displacement, and therefore there's no work being done. So, work is an interesting concept, and it's very, very important. However, from a general public perspective, work doesn't have a lot of meaning. What's more important is really what you can do in a certain amount of time. And so doing this in a certain amount of time is actually a much better, much more useful thing to know, because what it does is it actually puts together the idea of work with the idea of impulse, right? So remember, work is force times displacement, and impulse is force times time. And so as a result, putting the displacement and the force and the time together is actually very, very useful. And as a result, we get this idea of power. And so here's the definition. Power is the rate at which work is done. So you can, it's very simple formula. Look at this. Power equals work divided by time. That's it. So easy. There's not much to it. Just a quick note about units. Power is measured in watts, but watts actually comes from joules per second. Joules itself is a derived unit, which comes from newtons times meters, and so technically, watts is newtons times meters divided by seconds. Interestingly, if you see that there's meters divided by seconds in there, you might remember that that's actually the units for velocity. And so an alternate form of the power formula, although it's not listed there, is this. Power equals the amount of force done, or applied, multiplied by the velocity that is caused by that force. So P equals FV is actually a fairly common way to see power written out. There's also other power formulas as well. Specifically, there's electrical power formulas. There's power formulas for other situations, but really these two are the ones you're going to see most often. This is the one that's on the formula sheet right there, and then this one is kind of a useful shortcut. Where I took newtons times meters and then divided by seconds here and just broke out the meters per second as velocity. So either way works. Either way they're measured in watts. It doesn't really matter what formula you use to figure out the power. It's measured in watts. So let's take, for example, a light bulb. Okay, so I'm going to go ahead and draw a light bulb here like so. Right? This is the sort of old style light bulb. Because I'm old. There you go. And when you turn on the power, the light bulb puts out a lot of light and heat. And that light and heat come from the fact that there's an electrical current going through a very thin, high resistance wire inside the light bulb. Again, this is an old style incandescent bulb. So the light and the heat are actually forms of work. There's actually work being done. And so all of the stuff that you see coming out here, that's all part of the work that's being done by the light bulb. You could say, if you wanted to, that it's the electricity that's doing work as it goes through this part of the circuit. It doesn't really matter. So long as you understand that that's work being done, you're going to understand where I'm going with this. So if you figure out how much work is done generating all that light and heat, and you divide it by the amount of time that it takes, you end up with the power that is dissipated by the light bulb, the power that it uses every second, right? And so you are totally familiar with this because when you go to buy a light bulb, what you look for its brightness, and its brightness is measured kind of in watts. That's probably where you're most familiar with that. What are they actually telling you when you buy a 60 watt light bulb? You're saying that the circuit is doing 60 joules of work every second. And so 60 joules of light and heat energy are being used up by this little filament right here. It looks like this, like so, that, as it glows. So the electricity flows its way across that little filament. And if it's a 60 watt light bulb, that means 60 joules of work is being done by that electrical circuit, or that electrical current, every second. And so you can see that the more wattage, the more power, the brighter it's going to be. And so that's how we rate those. It's weird to think that light bulbs are rated in a power scale, because power is kind of I don't know, it's not immediately apparent that that's what it's actually measuring. You would have thought that it was measuring brightness. Brightness is really measured with other types of units in physics, depending on what part of physics you're studying. And we'll get to that when we get to light. But for right now, it's important to understand that the electrical work being done per second is actually what you're measuring when you buy light bulbs. Now, this was extremely important back when they were trying to develop steam engines, and so that's why Watt got his name attached to the units, because he was important in making the steam engine into something that was actually useful and efficient. He didn't invent the steam engine, but he did make it something that we could actually use. And so it's kind of important to remember the historical aspect of things, because the amount of power that a steam engine has is the amount of work that it can do every second. If I'm going to a farmer, which Watt did, or people who worked for him did, if I'm going to somebody who does a lot of work with animals, let's say I have a field, I need to plow it, and so I know how much work a horse can do in a certain amount of time. It's important for me to be able to sell the new engine in such a way that people understand what I'm talking about. And so in the United States and in England, where the Industrial Revolution really took hold the strongest, initially at least, we came up with this unit called horsepower. And horsepower is an attempt to sell people engines based on the fact that they do an equivalent amount of work per second as so many horses. Now, don't ask me who decided that one horse can do 735 joules of work every second. Don't ask me. I have no idea. It doesn't make any difference. What is important is that it was decided that that was the case, and then as a result, for sales purposes, we went ahead and developed this unit called horsepower. And so in the United States, for engines, we use horsepower still to this day as a way to measure the amount of work that an engine can do every second. In other words, its power. But you can see the equivalency right here. What that means then is we, in the United States, use watts for some power measurements like electricity, but we use horsepower for engines. And so it's a little confusing that we use a little bit of the metric system and a little bit of the imperial system, but we do. Unfortunately, we have to be careful about that. Okay, so oftentimes when non-physicists compare two systems, they're actually comparing the amount of power that something has. So I put this little weightlifter guy in here because I wanted to make sure you understood this. So he's doing work as he is applying a force upward on this barbell right there, and he is lifting it to a certain height, like so. And he does it in a certain amount of time, right? And so as a result, we can go ahead and measure his power. And so if we wanted to, we could talk about the most powerful lifter. And really, the most powerful lifter is really has to have one of these three things. If everything else is constant, then they have to be able to apply the largest force. Or if everything else is constant, they have to be able to lift it for the largest amount of distance. Or if everything else is constant, they have to do it in the shortest period of time. Shortest because time is on the denominator of the fraction, and so it must be the smallest to make power the largest. And so that's how the power equation works. Hopefully that makes sense. There is one possible area of confusion, and we have to be careful about this as we're starting to get into an area of physics where we have a lot of variable and unit issues. So, for example, we have power, capital P, and we have momentum, little p. We have work, and we have watts. So this should be in italics, and this should be not in italics, and that's why it's one of the reasons why I try to put things in italics like I did right there, and then compare that to the non-italics right there. And so we have to be careful about that. We had joules, and we have impulse, right? And so we have to be careful about how we, what we're talking about. So just be careful when you go through this, that when you see a W, you're really asking yourself, which W are we talking about? Are we talking about watts here for power, or are we talking about W for work? If you see a capital P, make sure it's capital P and not a lowercase p, because one is power and one's momentum. And then if you see a capital J as a unit, it has nothing to do with impulse. It has to do with joules. Okay, so be careful. All right, I think we're done. If you have any questions, please let me know. Thanks for watching.